Okay, good morning to everybody and welcome. We have the pleasure this morning to have again with us Professor Takaaki Kajita, and he will give us the second lecture now on a path to discovery, telling us his involvement in the gravitational waves. Thank you very much.
Okay, well, thank you. Good morning. Well, first of all, I have to, I think, apologize. Well, if I follow the website strictly, I have to mention, well, I have to talk about the path to discovery, gravitational waves. Well, I'm not the person who can discuss this issue. Therefore, I'd like to modify the title, that is Gravitational Waves and the Kagura Project. Well, okay, so at present, there are 4 large projects going on. There are 2 large interferometers in United States, that is LIGO, and they discovered gravitational waves. Then in Italy, near here, there is a Virgo laser interferometer, and they have been contributing significantly to the gravitational wave astronomy already. And the third one is the Kagura project. So I'm going to talk about the gravitational waves with these laser interferometers. Okay, this is the outline of this talk. First, I have an introduction on gravitational waves, actually on gravitational wave discovery. And well, in this part, introduction, I want to talk about the history towards the observation of gravitational wave as much as I can, but this is what I learned from various, say, websites and so on. Therefore, this is not a deep description of the discovery, but please forgive me. Then I want to discuss possible sources of gravitational waves. And before moving to the Kagura project, I'd like to briefly discuss the how we detect gravitational waves. And well, I also want to mention how difficult it is. Then I want to move on to the Kagura project, gravitational wave network. And also I want to briefly discuss the Kagura's contribution to the gravitational wave science and future and summary. Okay, now, as you all know, in 1916, Albert Einstein predicted gravitational waves based on his theory of general relativity. And well, this is the image of the gravitational wave emission from a binary black hole system. And well, these black holes merge, and a new heavier black hole should be created. And we'd like to observe these phenomena. Well, the theoretical prediction was more than 100 years ago. But if there is a theoretical prediction, and well, at the initial stage, people thought this could be really a theoretical thing. It may not be, some people thought it may not be possible to observe gravitational waves. But in any case, if there is a theoretical prediction, there are people who'd like to try to observe gravitational waves. Indeed, Joseph Weber made this kind of detector to observe gravitational wave. And indeed, in 1969, he reported that he observed a signal consistent with gravitational wave. Well, he had 2 detectors in a separate location, and then at the time, these two detectors observed a consistent signal. And well, okay, that was an interesting event. And indeed, this report triggered other people to do similar things. But no one was able to observe similar signals. However, I think this experiment motivated the detection of gravitational waves. Well, then the first detection of the gravitational wave came from a completely different observation. Well, there's a binary neutron star system, PSR 1913 plus 16. And in this system, two neutron stars or two pulsars orbit each other with an orbital period of 8 hours. Well, okay, maybe this is not necessary. Then Hulse and Taylor observed the orbital period. Then they found orbital period is getting shorter. And that means somehow the energy is, well, released from the system. Otherwise, it's impossible to change the orbital period. And indeed, the data gave very good agreement with the prediction by general relativity. And well, so this was indeed a very important observation. So gravitational waves exist. And therefore, they received Nobel Prize in Physics in 1993. And according to the Nobel Prize website, they say Hulse and Taylor's observations, although indirect, provided a strong proof yet for gravitational radiation. Their findings have provided the impetus to develop a series of gravitational wave detectors which aim to catch gravitational wave radiation from astronomical phenomena like black holes or to merging neutron stars through more direct means as their passing waves wash over the Earth. Okay, so already at that time, people knew that gravitational waves indeed exist, but of course, people would like to observe directly gravitational waves. Well, then a serious consideration was made by Ray Weiss. The Weber's detector 2 pages ago, no, 3 pages ago, had a disadvantage that the frequency of the gravitational waves that can be observed was limited to the resonance frequency. Therefore, in 1972, Ray Weiss proposed a laser interferometer to observe gravitational waves. And well, this is the Ray Weiss report. And if you visit this report, then you find this kind of sketch of the laser interferometer. And here is a beam splitter, and here is the here and here are the arm cavities. And indeed, already the Fabry-Perot cavity was assumed to get the high sensitivity. By the way, if we look at the history more carefully, we also find that these people thought about the possible detection of gravitational waves by laser interferometer. Anyway, based on his Ray Weiss's idea, there have been a long history. Already in 1974, Ray Weiss and Kip Thorne and Ray Weiss met Kip Thorne and convinced Thorne that a laser-based instrument would give them the best chance of finding gravitational waves. And they started working on the project that would become LIGO. And in 1979, the National Science Foundation found Caltech and MIT to carry out a feasibility study of interferometric detection. In 1985, the Virgo project was conceptualized by two scientists. Then in 1990 to 1999, the construction of LIGO at Hanford, Washington, and Livingston, Louisiana was approved, funded, and completed. LIGO is inaugurated in 1999. The Virgo project was approved in 1992 by the French CNRS and in 1993 by the Italian INFN. The construction of the detector started in 1996 at the Cassino site near Pisa and was completed in 2003. Then, between 2002 and 2010, LIGO began operations, but no gravitational waves observed. Virgo had several science runs between 2007 and 2011 without detection. Then both LIGO and Virgo had a long shutdown to improve the sensitivity substantially. And these projects are called Advanced LIGO and Advanced Virgo projects. Then, as you know, on February 11, 2016, there was a press conference. And at that conference, Dave Ritchie of the lab director announced that we have detected gravitational waves. And also, well, I would like to mention in this press conference, there was a talk by the director of NSF, Franz Cordova, and she mentioned since the mid-1970s, NSF has been funding the science that ultimately led LIGO's construction. And in 1992, when the NSF director, Walter Massey, and the National Science Board approved LIGO's initial funding. It was the largest investment NSF had ever made. It was a big risk, but NSF is the agency that takes these kinds of risks. Well, she proudly mentioned this. Well, anyway, based on this discovery, as you know, in 2017, Nobel Prize were awarded to 3 scientists in LIGO. I forgot to include this picture, sorry. Well, okay, so this is the sensitivity history of LIGO, Virgo, and, well, including Kagura. As I mentioned, the LIGO project started around 1990, and they had the first observation run with this sensitivity that is more than 100 kiloparsec, not megaparsec. Then they gradually improved, and at this point, they stopped the observation and had a very significant upgrade, that is the Advanced LIGO project. And then they started the observation ran here, and immediately they observed gravitational waves. And Virgo started the observation in 2007, and several runs. Again, they didn't observe anything. Then they made an improvement, advanced Virgo. Then they joined the observation in 2017, and again, they immediately contributed to the detection of the binary neutron star mergers. Okay, well, now I'd like to discuss the possible sources of gravitational waves. First of all, I'd like to remind you, LIGO and Virgo observed already a total of 90 events before 2023. And well, here the blue circles show black holes and orange circles show neutron stars. So it's clear that most of them are binary black hole mergers, but there are several binary neutron star and neutron star black hole mergers. Then the question is, what science would like to achieve with these observations or with future observations? As I said, most of them are merger binary black holes, but we already learned that black holes, we already learned that these black holes are rather heavier than we naively expected. Therefore, we'd like to know how these black holes were created in the universe. I think, in my opinion, this is an important new question to be addressed with gravitational wave detection. Then we'd like to also observe merger of binary neutron stars, and we'd like to know, for example, if a black hole is created immediately after the merger of the binary neutron stars. For example, this is a theoretical curve, but depending on the neutron star equation of the state, after the merger, there might be some period where the supermassive neutron star exists, then collapse to black hole, or depending on the equation of state, essentially they immediately collapse to a black hole. And with the observation of the binary neutron star mergers, we'd like to know if heavy metals such as gold are produced during the merger of binary neutron stars. And of course, in 2017, the gravitational wave signal of binary neutron star merger was observed for the first time, and this observation partially confirmed the origin of them. But of course, we'd like to be more precise. For example, we'd like to know only binary neutron star mergers can account for the all existing heavy metals in the universe. Also, for example, we'd like to understand the short gamma ray bursts. So there are a lot of science with the merger of binary neutron stars. Well, of course, this is the signal observed in August 17th, 2017. This is the LIGO signal. Here, the frequency is plotted as a function of time. Then you see this kind of chirp signal. And at that time, as I mentioned, Virgo just started the observation, and therefore by combining the Virgo data, they were able to narrow down the source position. Therefore, astronomers try to observe the object to that direction, and indeed they find corresponding source. And then astronomers started to look at this source carefully. Then they find this kind of the light curve. So ultraviolet light disappeared soon, and infrared light stayed some time. And this was consistent with heavy metal generation. But as I said, we'd like to understand more precisely. And finally, we'd like to know how the heavy star finishes their life by observing the supernova explosion by gravitational waves. Okay, now I'd like to move on to the detection of gravitational waves. Well, I'm not going into details, but I just want to remind you the accuracy we need to observe gravitational waves. Well, here I plotted, here I show the sun and the earth. The distance is well known. Then, of course, if a gravitational wave comes to the solar system, the distance between the sun and the earth should change. The question is, how much distance change we expect? And the answer is, if a strong gravitational wave comes to the solar system, strong means the gravitational waves that can be detectable with the present generation detectors, the distance between the sun and the earth will change by about 10 to minus 8 centimeters. Well, of course, 10 to minus 8 centimeters is actually not extremely difficult to measure this kind of length change. But the problem is the present-day gravitational wave detectors have the arm length of only 3 to 4 kilometers. Therefore, these detectors must be sensitive to the length change of about 10 to minus 16 centimeters in 3 to 4 kilometers. So this is a challenge. This is an extremely small number. Therefore, well, I am not going into details, but we have to do everything what we should do. For example, we have to isolate the mirrors from the seismic activities. Therefore, we suspend mirrors, and this way we isolate mirrors from the seismic activities. Or plus, we may go underground to reduce the seismic activities itself. And the arm length should be as long as possible. And as I said, at present, the arm length of the laser interferometers are about 3 to 4 kilometers. But in addition, in every project, we use Fabry-Perot cavity to enhance the effective arm length. Well, by using this Fabry-Perot cavity technique, typically the effective arm length is say enlarged by a factor of 100 to 1,000. And of course, if the laser interferometer is located in the air, then we'll have a significant interference by the air. Therefore, everything is in the vacuum. Furthermore, well, after the interference, the weak interference light goes to this direction, but most of the light go back to this direction, which is actually a waste of the power. Therefore, we put power recycling mirror here and put the laser beam back to the system. And this way, we actually effectively increase the length or effectively increase the power stored in the fabrilary cavity. And finally, in some cases, we put signal recycling system, and this way, well, we can still enhance the signal. Oh, and we need, of course, stable and high power laser. And finally, of course, every mirror is made of matter, and therefore there is a thermal motion of molecules. And eventually, this could be one of the ultimate sources of the background. Therefore, in some cases, we use cryogenic mirrors to reduce the thermal motion of fluctuation of the molecules. So, well, we tried, well, in fact, in addition to this, nowadays, we try to use quantum optics technique to further enhance the sensitivity. Anyway, what I would like to tell here is we have to put every technique we have to enhance the sensitivity. Okay, now I want to discuss the Kagura project. Well, Kagura is an international collaboration, and these flags show the countries and regions that participate to the Kagura project, and you see, well, the majority of the collaboration are from the East Asian region. So Kagura is an international collaboration and mostly from the East Asian regions. Okay, so this is the image of the Kagura interferometer. First, whole Kagura instrument is located underground. I think, well, the construction of the interferometer, large interferometer in underground is not easy, but we have an advantage. In underground, the seismic activities are reduced. Therefore, the seismic noises are in general much smaller. In addition, we use cryogenic mirrors for the test masses here, 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 and here. And therefore, by using cryogenic mirrors, we reduce the thermal noises. Well, before discussing further details, I want to tell you my personal history. Well, as I mentioned yesterday, I was working on neutrino physics, but now I'm working on gravitational waves. Well, let me tell you why I changed my research topic. Well, as I mentioned, as I talked yesterday, I studied neutrinos for more than 20 years. Well, 20 years is a long period. And after the discovery of neutrino oscillations in 1998, and after some more studies for several more years, I was feeling that I finished what I should do in my neutrino research. Of course, well, neutrino research itself, there are many important topics to be done. But personally, I thought my role was finished. On the other hand, of course, there are still many exciting science that we'd like to study. And in particular, gravitational waves are not yet discovered early in this century. And I was fascinated by the research on gravitational waves and the studies of the universe with gravitational waves. Well, that means new ways to study universe. And well, in particular, I was Kagura in my mind. And, well, in my opinion, Kagura's mission was clear. Kagura should contribute to the gravitational wave astronomy as a detector far from LIGO and Virgo. This is actually a very important point for the accurate pointing of the source. Also, Kagura should develop the cryogenic technology and contribute to the next generation of gravitational wave detectors. Then, in 2008, I was appointed as the director of the Institute for Cosmic Ray Research, and it was clear that I could no longer contribute to neutrino research much because, well, essentially I spent really substantial time for the director job. But still, I wanted to be involved in exciting research. That means I don't want to be 100% director. So therefore, I decided to participate in the gravitational wave project Kagura with my partial time. But now, I finished my director job, and therefore I'm able to spend more time on Kagura. Okay, anyway, let me tell you what is Kagura. Well, Kagura is located here in the same mountain as Super Kamiokande. But, well, in order to go underground, of course, we need an entrance. But our entrance to the underground site is actually completely different from the entrance to the Super Kamiokande site. So actually, we want to be as small interference as possible with the neutrino activities. So this is the Kagura entrance. Okay, yes, and this is the history of the Kagura project. The project was approved in 2010, and then, of course, we immediately start the preparation and the construction work. Well, essentially, this work continued for about 10 years. And also, of course, we needed to excavate the underground site, including the 3 kilometer by 3 kilometer tunnel. And after finishing the initial construction, we started the commissioning of the laser interferometer, and we had the short observation in 2020. Then, after this very short observation, we came back to the improvement work and the commissioning, and it took us for about 3 years. Then last year, at the end of May, we joined the observation 4 or 4, but, well, Kagura's sensitivity was not good enough to really contribute to the neutrino astronomy, gravitational wave astronomy. Therefore, we came back to the commissioning. And we are here today. So I want to show you several photos from now on. Well, the first work was of course, to excavate the underground tunnel and the site. After that, we installed these 3 kilometer by 3 kilometer vacuum tubes. Well, it has a diameter of 80 centimeters, and therefore, well, compared with the LIGO, our vacuum tubes are slightly narrower, but we think this is not a problem. Oh, by the way, well, in order to have a very good vacuum in underground, well, typically, in order to get very good vacuum, you need to raise the temperature of this vacuum tube, and with the outgas, after the outgas, you achieve a very good vacuum. But it is not possible for Kagura to do this kind of operation. Therefore, we use the accelerator technique. They have a very good technique to achieve high vacuum, and therefore we had used this kind of technique in constructing the vacuum tube. And this is the central area. In fact, this is the beam splitter. And well, in the right, there is a laser source, and then laser come, and the beam is split to this direction, to this direction. And well, in fact, in this plastic tent, there are several, well, you can see several vacuum tanks. But well, and therefore, as a photo, this is not very, very nice. But well, we need this kind of plastic tent because this is a clean booth. We have to work under extremely clean environment to install the mirrors and vibration isolation systems. And in fact, in the clean booth, we installed the mirrors and suspended by vibration isolation system. Well, these two are the examples. And this is one of the main mirrors. This is a sapphire mirror, which has 22 centimeter in diameter and 15 centimeter in thickness. The weight is 23 kilograms. And this is actually a photo taken during the preparation of the mirror. And after finishing the preparation, this mirror went into the Kagura site. And after finishing all the installations, everyone was requested to go outside. And the laser interferometer was operated from the surface building here, this one. Okay, now I want to mention about the gravitational wave network. Well, first of all, this is the map of the gravitational wave laser interferometers. And important thing is to determine the location or direction of the source, we need at least 3 detectors which are located far apart from each other. Because, well, every single detector, even if it has a very good sensitivity, it cannot tell the source direction. Therefore, we have to use the signal arriving timing to estimate the source direction. And in order to do so, we need at least 3 detectors far apart. And therefore, the existence of Kagura, which is far apart from LIGO and Virgo, is very important. And therefore, Kagura decided to join the network observation with LIGO and Virgo in 2019. And we are working together, namely, we observe gravitational waves simultaneously and analyze the data as a team. Now, I'd like to briefly tell you about the story around 2020. In March 2020, after about a year of very intense commissioning, Kagura achieved the sensitivity of 1 megaparsec, which was the requirement to join the global network. And indeed, we achieved in March 2020. and officially joined the gravitational wave network with LIGO and Virgo. But at that time, of course, we had COVID-19. Well, Kagura had 2 weeks observation but gave up because no one outside of the observatory came to the site. Therefore, only site people operated the detector, but 2 weeks was the maximum. They gave up. And therefore, after stopping the observation, we started the improvement work. So, well, in the 3 years, we again worked on the hardware improvement. We reinstalled the vibration isolation system. There have been many problems. Of course, then we have to test the system, and also we reinstalled the output mode cleaner and so on. There have been actually many problems. Therefore, we had many things to do. Then, so this is the official observation history and plan of LIGO, Virgo, and Kagura. This was the 2023 version. So, well, following this schedule, Kagura joined the observation on May 24 last year. And in fact, compared with Kagura in 2020, the sensitivity was improved. And also, in fact, the operation was very stable compared with the 2020 Kagura operation. But, well, this sensitivity was not high enough. Therefore, after 1 month of the observation, Kagura stopped and restarted working on the sensitivity improvement. And Kagura has been planning to rejoin the observation with higher sensitivity in the spring of 2024. That is essentially now. Then, well, on January 1st this year, a local earthquake, magnitude 7.6 earthquake occurred here, which is about 100 kilometers away from the Kagura site. And this is the seismic intensity based on Japanese seismic intensity scale. And, well, the local city, Hida city, is here, and the data indicate that this earthquake was the strongest one in Hida city in the last 100 years. And in fact, the Kagura surface building was like this. Well, so this was actually a serious issue. But, well, we think we were fortunate because we installed the Kagura laser interferometer in underground. And the effect of the earthquake was significantly smaller in underground. But unfortunately, there were still many damages in Kagura. And therefore, we started the recovery work in February, and we are still in the middle of the recovery process. We essentially finished the recovery by hardware, but from now on, we have many things to do. We need to align the laser interferometer, and we need to restart the commissioning, and we hope that Kagura can rejoin the observation and contribute to the gravitational wave astronomy as soon as possible. Hopefully, that is in the best case scenario in early next year. Okay, I'd like to briefly discuss Kagura's contribution to the gravitational wave science. Well, first of all, I would like to show you this view graph. This shows the direction that each laser interferometer is sensitive or very bad sensitivity. And these are two LIGO laser interferometers. Here is Virgo and here is Kagura. And then you find Kagura is actually is complementary in the sensitive direction to other detectors. Therefore, I think we should contribute as much as possible, as soon as possible, to the network observation. In fact, if there is no Kagura, then the overall sensitivity direction map is like this. So if we have only LIGO and Virgo, there are several directions that has very bad sensitivity. But if we have Kagura, then except for these two small locations, we expect a very good sensitivity to all directions. So that again tells us the importance of Kagura. And indeed, if we assume neutron star merger at 150 kiloparsec with the design sensitivities, then by adding Kagura, the gravitational wave detectors can predict the source direction with much higher accuracy, maybe a factor of 3 improvement compared with no Kagura case. So I think, again, Kagura's contribution should be, we should contribute as soon as possible. Okay, well, that's all for Kagura. Now, in the next few minutes, I would like to briefly discuss about the future ground-based laser interferometers. Well, since the present generation of ground-based gravitational wave detectors have been so successful, there have been intense activities to design and propose the next generation detectors. One is the Einstein telescope in Europe. Another is the Cosmic Explorer in United States. And these future detectors, well, at least Einstein telescope, will use cryogenic mirrors to improve the sensitivity. And one of them, Einstein telescope, will be constructed in underground for the better sensitivity. Therefore, I think Kagura can contribute to these projects by the experience of the underground site and the technology in the cryogenic mirrors. By the way, so these are really big projects. Einstein telescope, according to this design, the baseline length is 10 kilometers, and the facility is this kind of L shape. And the Cosmic Explorer is even bigger, 40-kilometer baseline length. Now, the sensitivity of the future gravitational wave detector is really, really impressive, in my opinion. Here, the horizontal axis is the total source frame mass, and the vertical axis is the redshift. So here is the reach of the Cosmic Explorer, and green one is the reach of the Einstein telescope. You see that these projects essentially reach redshift 100, although the mass range is limited. So that should be extremely important. Of course, we do not expect well, according to the standard idea, we do not expect any gravitational wave signals from these redshift regions. But, well, of course, no one knows. So this should be really an exciting project to me. Okay, one more slide, okay. But before finishing, I want to mention, well, yesterday I talked about the neutrino physics, and today I discussed gravitational waves. But I want to mention that they should not be independent. For example, if a supernova explodes at the center of the Milky Way galaxy, then of course we should observe gravitational waves and neutrinos. And by combining these two information, we think we truly understand the detailed mechanism of the supernova explosion. So I think we should work together, neutrinos and gravitational waves. Okay, let me summarize. There are very interesting history in the detection of gravitational waves. Gravitational wave astronomy is a new and exciting scientific field, and many more fundamental discoveries will be ahead of us. And Kagura is a unique gravitational wave detector with cryogenic mirrors and the underground site. And, well, of course, Kagura would like to recover as soon as possible from the damage of the earthquake and contribute to the gravitational wave astronomy as soon as possible. Okay, that's all from me. Thank you very much. Yeah.
Hi, thank you for the talk. This might be a silly question, but I was just wondering, so if I understand correctly, Japan has a lot of earthquakes. If you have another one after you fix the damage that Kagura has, what will you do?
Thank you. Yes, thank you very much. Well, certainly this was the strongest one in the 100 years. Therefore, we do not expect this could occur too frequently. But of course, well, since we experienced this kind of damage, we would like to improve the detector system a little bit. First of all, well, actually, in the earthquake, about half of the vibration isolation system was damaged. But if we look at the damage more carefully, we found that some of the systems were actually okay, but some of the systems are badly damaged. In fact, therefore, we think we have to improve this weak system. And in addition, well, one of the systems actually, well, in most systems, we suspend mirror from the top. But in one of the systems, we use the, say, plate and rubber system in order to reduce the seismic activity. But it seems the rubber was crushed. So maybe it takes really a lot of time to recover because everything was on top of this system. And therefore, in the future, we may have to think about the better system. But, well, I think it takes some time. For the present recovery, we have no time to put new system in. Therefore, we simply recover, but toward the next observation run, we start improving the system.
Thank you for the very nice talk. I was wondering why the sensitivity of Kagra is smaller than the sensitivity of...
Yeah.
Even from the very beginning, you showed this plot that the sensitivity has improved over the years, but...
Well, actually, I think well, I think this history tells us. Well, of course, our design sensitivity is similar to LIGO and Virgo, but in order to achieve the design sensitivity, we have to do everything as perfect as we wish. And in fact, typically, in order to fine-tune the vibration isolation system, it takes time. Well, in fact, last year, the sensitivity was not very high, but after that, people had an intense improvement of the vibration isolation system control system. And therefore, already at the end of the last year, we were convinced we reduced the noises related to the vibration isolation system by a factor of at least 25. So, in order to get the good sensitivity, we need time. We need experience.
Okay, thank you.
Concerning this supernova synergy, one obvious possibility is elastic scattering on electrons, which will be directional. This, probably was not of supernova 87, but surely will be detected. So question is, how much time you will need before releasing the trigger? Because, this will be very strong psychological advantage also, because supernova will not be seen with ice, but will be seen with gravitational wave and with neutrino.
Well, thank you very much. Well, okay, so, but today I'm talking about gravitational waves, but switch back to the neutrinos. Okay. Well, actually, well, first of all, now we have the SNUS system, that is the neutrino detector network. And well, last week we heard that now SNUS had implemented a new feature that is combining the arrival time information by various detectors. They'd like to estimate the signal arriving direction. That is one thing. Another is a gravitational wave. Again, by combining various detectors' timing, we can estimate the arrival direction. But the question is, how long will it take to issue the alarm? For this, actually, I'm sorry, I don't know.
Okay, let's hope for the best.
Yes, thank you for your very interesting lecture. I was wondering if for the Kagra project you adopt the same techniques to reduce thermal noise, seismic noise, like in advanced LIGO and Virgo, and in particular if mirrors are suspended by using silica fibers like in the other detectors. Thank you.
Sorry, what was the question?
If you adopt the same techniques to reduce noise like in advanced LIGO and Virgo, and if mirrors are suspended in the payload by using silica fibers.
Oh, I see. Instead of the sapphire mirror, what will happen if we use the normal silica mirror and normal silica fiber? Is this the question?
Yes, yes.
Yeah. Okay, thank you. Well, certainly in this case, around 100 hertz, we may soon or later come to the thermal noise limit. But in the 100 hertz region, if in our case, we can still go down. And in fact, well, this may not be realized actually, but in fact, in the designing stage, we have been thinking to get very high sensitivity around 100 hertz resonantly by a special technique so that we can have the best sensitivity around 100 hertz. But well, nowadays, we may not have so much interest in this possibility. And so in that sense, well, certainly it was in fact possible to use the normal silica mirror, normal silica fiber to achieve an equally good sensitivity with much less effort. But anyway, this was our choice.
Thank you, thank you. Other questions?
And thank you for the lecture. I'm afraid that it's not really strongly related to physics itself, but I feel so sorry about the earthquake. And I remember that it was New Year, so that were people working on the site at the time of the earthquake, and how was it damage of the people?
Well, thank you. Well, first of all, it was fortunate that no one was damaged. That was okay. And actually on that day, there seems to be several people there and experienced a huge shaking. Yeah, that's all I can tell.
And also, what about the damage of the neutrino experiments there?
Neutrino experiment was okay. Well, okay. Super Kamiokande was operated, and I heard in Super Kamiokande there is a water level monitor, very precise, and in fact, this monitor recorded this kind of waves, and in fact, the effect was much larger compared with the 2011 great earthquake in Tohoku. Oh, by the way, related to your question, actually I want to mention, well, now we are thinking about the possible future upgrade, and for this, we are thinking to actually want to use the advantage of the cryogenic mirrors. For example, these sapphire mirrors has a very good thermal conductivity. Therefore, it is possible to remove the heat efficiently from the system. And that means it is possible to inject high power into the interferometer system. And this way, maybe we'd have to have a unique contribution in the future gravitational wave detection.
Thank you.
Other questions? Okay. So if there are no more questions or comments, so let us thank Professor Kajita.
Thank you.